Hello and welcome. I'd like to welcome you to what I'm going to call Chapter 1.2, Mathematical Models. Models and Essential Functions. I would like to start out by just doing a small bit of review, and I want us to find what the slope of the secant line for y is equal to 1 over x plus 3. So you may remember that the slope of a secant line is going to be given by f of x plus h minus f of x all over h. So let's do that with this equation. So we are going to get, and I'm just going to pull out the 1 over h out front just to make life a bit easier. So this is going to be equal to, so we have 1 over x plus, no, that's not equal to, this is times, x plus h plus 3 minus 1 over x plus 3. Now how are we going to evaluate this? Well, let's multiply the top and bottom of both the fractions here by this one by x plus h plus 3, and this one times by x plus 3 times by x plus 3. Sorry, that's gonna get a small bit crowded. X plus 3. There we go. So on this left-hand side, we are going to get x plus 3 minus x plus h minus h, sorry, plus h plus 3. Let's just put you in parentheses, make the cleanup a bit easier over. X plus h plus 3 times by x plus 3. Okay. M is now going to be 1 over h times by, well, let's see, this denominator expands out to x plus 3 minus, I don't need the parenthesis there anymore, minus x minus h minus 3. And I am just going to leave the denominator like this. So let's see, the x's will cancel and the 3's will cancel. And would you look at that? We are left with just 1h in the numerator. So this, whenever I cancel u and u, we are going to get negative 1 over x plus h plus 3, and then x plus 3. And that's going to be our slope of the secant line for x and then any given of h. So, now that we've done a small bit of review, let's talk about what is a mathematical model. So, a mathematical model is a mathematical description of something that happens in the real world. That happens in the real world? Well, I think a question that's a very commonly asked one among high schoolers, college students alike, is when am I ever going to use this? And I understand for a lot of people, they're not going to understand when we're going to need to know how to find the vertex of a parabola. Or they won't want to know how to solve exponential equations. That wouldn't be an exponential equation. This would be an exponential equation. But all of this are tools that we can use to create mathematical models of the world. And in fact, that's what calculus is somewhat about. Modeling the real world. Modeling change, in fact. So, algebra has given us this catalog of functions. And I think we should start out with the most simplistic. And that is going to be the form of a line. So, let's see. So let's see that this is our line. And all lines have the equation y is equal to mx plus b. But there's one more not so familiar equation that you might not know. And this equation is y minus y1 is equal to m times x minus x1. And you may ask yourself, why do we want this equation? Well, this equation is actually a lot easier to work with than, in my personal opinion, the y is equal to mx plus b. Because as long as we know any one point, for example, if we knew this point, we can plug that into this equation, and we would have an equation for x. We don't have to find this x-intercept. It also makes it very easy for solving for this m. All you need to do is know 2 points. So I think for the majority of this course, we're going to be focusing on this one just because it's going to be a lot easier for our applications later on. Y minus y1 is equal to mx minus x1. And an equation that, and a time that we might want to see this is if you are given points 2, 4 and point, let's see, 6, 7. We can plug in one of these points. Let's say that we want y minus 4 is equal to mx minus 2. And then we can now solve for m using our second point. 7 minus 4 is equal to m of 6 minus 4. No, 2, sorry. So in reality, we get m times by 4 is going to be equal to 3. So our slope is equal to 3/4. So our final equation for y is going to be y minus 4 is equal to 3/4 x minus 2. Okay, so that's going to be our linear model. Now, another model that we might want to get is polynomials. Polynomials are a very broad family of functions, and in fact, lines technically are polynomials. Although they aren't normally classified as such. So, polynomials take the form of y is equal to p of x, and that would be equal to a to the n. And this is a subscript n. It doesn't actually, it just means like this is a certain n, to x to the n plus a to the n to the x n minus 1, so on and so forth, until you reach your last a and your x is 0. So a naught x is 0. And we have a lot of different polynomials out there, but polynomial n has to be an integer. A integer. And polynomials have a few very nice properties that we get to work with. Their domain is always going to be all real numbers. No matter what value of x you choose, there's always going to be an output y. And if there's not, then it's not a polynomial. Power function. No. Yes, power functions. So this is really like we're tearing apart a polynomial, and power functions are going to take the form p of x is going to be equal to some constant times by x to a power n. And now power functions have to have n as a positive integer. And really they have all the same properties as a normal polynomial. The next type of function that is closely related to power functions are root functions, where p of x is going to take the form c times by x to the power of 1 over n, where once again n is a positive integer. So these are where you can start getting a restricted domain. And for example, we're going to do our principal root function, which is the square root of x. It has no unreal values for negative x's. So if you plugged in like -2, you wouldn't get a valid output. There we go. However, this is largely dependent on the domain of its parent function. Or sorry, it's a range of its parent function. For example, you can also have the cube root, or x to the power of 1/3. And in that case, x is going to look like something on the lines of this. So its domain is going to be all real numbers. And you just really have to be careful. But for a general rule, if n is odd, the domain is all real numbers. If n is even, the domain is going to be greater than 0. X greater than 0, sorry. Continuing on, we have another form of function, which are the reciprocal functions, that take the reciprocal, I don't know if I spelled that right. Alright. I am going to just say that I think I did. And no. Okay. Alright, I'm back. I got it. So, a reciprocal function is a function that's called r of x, where it is a polynomial divided by a polynomial. Polynomial. And these are where you can get some really cool graphs with some very interesting features. For example, you can get graphs that almost look like a line but have holes in it. You can also get graphs with humongous horizontal or vertical asymptotes. There we go. You can also get graphs with slant asymptotes. So that would kind of look like, let's see, so let's say that there's a vertical asymptote there, and then, yeah. You can also get horizontal asymptotes, but these are some of the most unique functions that we have. But I think there's a few more unique ones. All of the functions that I have described as of thus far are algebraic functions. Algebraic functions. Algebraic functions are functions that can be constructed using algebra. Algebraic operations, rather. Algebraic. Just scratched that word there. Algebraic functions. And these are things like addition, subtraction, multiplication, division, and raising things to a power, which I'll do a caret to an n, or doing square roots, or doing roots. All of these things are algebraic functions. Now, you might notice that there's a few functions that you may have learned already that aren't on this list. And we're about to go over them. These are called the transcendental functions. Transcendental functions. These are functions that cannot be represented by algebraic functions. By algebraic functions. Alright. Now, let's see. The first type of these that we're going to go over is trig. Oh, so many people in my classes have hated trig. Me, I love it, honestly. Trig functions are based on right triangles. And there's a lot of trig functions. And I mean a lot. That was not a very good right triangle, but kind of hard to draw perfectly. There we go. It worked. All of the trig functions are based on this triangle here. And they are given in theta, where theta is in radians. I'm going to make an entire separate video for trig, and the reason for this is trig functions are by far like one of those things that you have to understand for calculus, but I'm going to give us a small bit of like a understanding here. For example, I want us to evaluate tangent. Well, actually, first let's give you a catalog. So all the trig functions that we have are going to be cosine, sine, tangent, cotangent, cosecant, and then secant. And I'm going to zoom in just a tad here, and you'll see why. The domain of each of these, cosine is all real numbers. Sine is all real numbers. Tangent, however, is where things start getting choppy. Cosine, or the cosine in it, because it's going to be sine over cosine, cannot be equal to 0. So it's all real numbers, but x cannot be equal to plus or minus, or sorry, yeah, plus pi over 2 plus 2 pi n. And sorry, that is a small bit of a mess. I think I'm going to draw down my size just a small bit. Temporarily show favorites bar. Yes, please. Cotangent is similar. But in cotangent's case, sine can't be. So in reality, it's just all real numbers. But x, sorry, cannot be equal to any 2 pi, or, sorry, this one's every pi n. No! 2 pi n. This one down here is pi n. I lied to you, I'm sorry. Pi n. So cosecant is also has a domain of all real numbers, although x cannot be equal to, whenever sine is equal to 0, sine is equal to 0 at every pi. So this one, again, is pi n. So secant, on the other hand, is x cannot be equal to the same rule as tangent, which is going to be pi over 2 plus pi n. And these are some basic trig. If you've done trig before, then you're gonna obviously know a lot of this. And then we have a lot of more interesting functions. For example, we also have cosine inverse, sine inverse, tangent inverse, cotangent inverse. Sorry about the cosecant inverse, and cotangent inverse. However, I want to talk about all of this stuff right here, this stuff down here, in more detail in another video, as I will not give it enough justice. I will also go over some more trig identities inside those videos, as I feel like those are also useful to know for calculus. However, for those of you that do know trig, I would like to go over a small bit of trig, just as a nice review. Let's see, I want us to evaluate tangent of pi over 3. So the way that we're going to do this is we can break tangent down into sine of pi over 3 and cosine of pi over 3. We know that sine at pi over 3 is going to be square root of 3 over 2. And we know cosine is going to be 1/2. So I'm just going to do myself a favor and call that 2. And we now get tangent is equal to the square root of 3. Let's now do cosecant of pi over 4. Yeah, pi over 4. Cosecant is the same thing as 1 over sine of pi over 4. And we know sine of pi over 4 is square root of 2 over 2. So if I just move this 2 into the numerator, divide it, we would get square root of 2. And the final thing that we're going to do is we're going to look at tangent, or actually no, scratch that. Let's do a cosine of 7 pi over 6. So this is going to be a bit more challenging. But this is going to be, well, let's think about it. So we know pi over 6, cosine of pi over 6 is square root of 3 over 2. And we know that this is going to be in the back. We know that this is going to be over here in our unit circle. So we know our cosine is going to be negative, so that's going to give us a negative square root of 3 over 2. Continuing on, let's see. Our next favorite type of function that we're going to go over is our exponential functions. The exponentials and functions. Honestly, some of my favorites are here. I don't know why, they're just really nice functions to work with. So an exponential function is a function that will take y is equal to a to the x, where a is a constant. If a is less than 1, sorry, not 0, then this is going to represent decay, or it's going to get smaller over time. If a is greater than 1, it's going to represent growth. The domain for all exponential functions is all real numbers. So these functions are really useful for modeling things like compound growth, or compound interest, sorry. Compound interest. And growth. And population growth, more specifically. So if I wanted to know how much money, let's see, if I invested a principal amount, let's say $1,000, into a bank account, and it got 3% interest rate a year, so we're going to say that it's going to keep the original one and get 3 more percent, and it's going to get, what's it called? And this up here is going to be the year. This is going to be a model of how much I'm going to have in my bank account in however many years. So if I wanted to know how much money I'm going to have in 10 years, well, we're going to look at it. We're going to plug in 10. And of course, that's not a very nice number to work. So we get out our calculators. I would recommend having a calculator for calculus. That's just kind of a side thing, but it is recommended. And we would see that 1,000 times by 1.03 to the power of 10. And we'll see that in 10 years, I'm going to have $1,343.92 in my bank account. Looks like I got $343.92 just from letting my money sit there. Adding on to this, we also have the brothers of the exponentials, the logarithms. Logarithms. Logarithms are equally as useful as exponentials for a variety of reasons. And one of which is they are the inverse to the exponential. In fact, if we just draw out a graph, and we're going to say that this and this are both 1, and we have a line here that is y is equal to x, because that's what the inverse does. It flips our y's and our x's, so it really just flips it over the line is equal to y equals x. We are going to see that this right here is an exponential, and this right here is a logarithm, and they are perfect inverses. And this holds true. Their domain is actually swapped with their range. For example, the range up here for an exponential function is, sorry, it doesn't include 0 to infinity. And we see that our range our domain down here is 0 to infinity. And our range is all real numbers. All real numbers. Sorry, that's a very messy all real numbers. So you can see that these functions are truly inverses of each other. They have the same domain and the same range. Now, let's start talking about how they look. So logarithms have a look that looks like, or actually rather, the way that I'm going to say this is, let's start out by saying that we have a to the y is equal to x. In fact, this is just an exponential. So let's try, well, you know what? Scratch that. We're going to do the inverse the normal way. So we start out with y is equal to a to the x. Then, to find its inverse, we are going to take, say that x, put in x's for y's and y's for x's, is equal to a to the y. Okay. Well, how do I get this y out of the power area? Well, we're going to take the logarithm of both sides. And let's just call this log base a of x. And because we're taking a logarithm of a, and a is raised to the y power, the only thing that's going to be left is y. If that makes sense. So the logarithm is this inverse to the exponential. So it has a lot of useful properties. For example, it can be used to solve exponential functions. But it can also be used in its own forms of modeling. In fact, it can be used for modeling population growth. And so much more. It is an incredibly useful tool. And we'll talk some more about properties of logarithms in another video after the trig, as well as we're going to talk some more about exponentials in another video. But I want to thank y'all for watching. I hope y'all have a wonderful rest of your day, and I hope y'all enjoyed and found this informative. Have a wonderful rest of your day. Bye-bye.